Okay, so I take you back to deep learning again. There is no escape. So the three works that I'm going to present, they are with my research team, Bashar, Thiru, and Sharon. So I'll be touching upon all kind of data sets. So in the first method that I would describe, it would be about textual data. The second method would cover the numerical, the record standard kind of data. And the third talk would be the longitudinal data, temporal. And in all these methods, we are dealing with the lack of data. So we are not starting from no data, but as we know, the machine learning and specifically deep learning models, they require a large amount of data. So what happens when we don't have too much data to improve the model quality? So what methods can we use to complement that data so we have improved and accurate classifiers? So that is the running gist behind all the methods. So the first method that is based on text data or the natural language processing, and it becomes easier when we are dealing with the text data because as we know, there is already a pattern that occurs in any of the languages. And if we consider English as a language, there is a strong pattern. So now the question is, how could we capture that pattern and then use that pattern to complement the lack of the data that we have for a particular problem? So for example, the problem could be misogynistic tweet or misinformation tweet or biased tweet like gender, culture, racial kind of detection, or even the cybersecurity threat intelligence. So we have got heaps of tweets or social media posts, but the problem is how do we get them labeled? And if we are doing the manual labeling, they are always introducing bias. So the idea is to get a small amount of labeled data, but then use the techniques that can deal with this short amount of labeled data. And we can still build a classifier that is quite highly accurate. So in our research group, we have been working on this problem from the last 3 years or so. And we proposed this concept of progressive transfer learning that could learn from data set. Those are related to the problem that we are studying and then transferring those patterns to the problem that we are saying. We saw this kind of network in Fiona's slide as well. So as we all know, let X be a text data set and CK or K would be the classes. So the objective of any classifier is to build a search space or the boundary space where we can actually learn the probability of a class given an instance. And it is important for us to know this conditional probability of the data set of the class given X. So the joint probability of X and CX can be written as this probability of CX given X and with the prior of a data set distribution. So essentially, we can see this one as the conditional probability, and more specifically, that the prior probability is essentially regularizing this probability of CX given X. The more important point here to note is the prior probability X only depends on the data input. It is not depending on the class of the data. So that's where then we propose that we can actually take advantage of any unlabeled data that is relevant to the domain and utilize that data to transfer the patterns. So, and this problem essentially works for the large data set like LSTM, long short-term memory data set. So these discriminative models, when we are working for a problem that is quite complex, but we don't have enough labeled data set. So it could be the misogynistic tweet detection, where the problem is complex because we are trying to learn from the context that is inherent in tweets without actually relying on to the specific words that directly indicate the misogynism. These deep learning models try to approximate the population distribution, learning this theta as model parameters. And when we have a small level data, there is a probability of overfitting it. So what we try to do, we try to learn this prior probability using any unlabeled data. And the way that we do it, progressively, it learns the capture. So it becomes important in terms of what kind of data set we capture. So in our work, we have extensively showed and proved that when we go from generic to a specific domain, we actually capture these knowledge patterns within the data set quite correctly. So for example, in this particular problem, we started D1 as Wikipedia because it is a typical language expression in any language. So it learns the language expression. Once it learns the language expressions, we actually fine tune it to another model that may have some abusive content. So it could be movie review data set. And there is no lack of these unlabeled data that exist in social media public posts. And once we learn the knowledge patterns and the abusive patterns, then the next task would be to learn the tweeting patterns, like how people tweet. So once we learn these kind of language, our language model had actually learned a lot about the language. Now it becomes a simple task to regularize this language model on a classification model that can be built now on a small label data set. So we have got extensive experiments, but I'm just producing some where it shows that when we regularize our classification models with these language models, actually the classification accuracy highly improves there. The second method that we have worked on fits into any kind of scenarios where we are considering data shifts or concept shifts or domain shifts. So we build a classifier model on a training data, but when we apply into practice over some years, there may be a shift in the data. So that model does not fit it. So now the question is, how can we really adjust that data or the model so actually it learns onto this new data? So this is the second problem that we dealt with. Usually in literature, they are called as closed set domain adaptation, open set and partial, where both source and target would share some of the classes. So we now deal with a new kind of problem, and that is quite a recent problem that may fit into many scenarios. And if we think about considering the ABS scenario, so ABS would get a large data informing about people's tax, income, their occupation, and so on. But the problem for them is that when they get this data, it's sometimes it's 18 months of lag. So it means that the feature of the data may not apply to the current population. And they can generate some of the current population by doing quick survey to some businesses and getting their current information. But now the problem is that the large data set, that is a big data set, and let's call it A, it is outdated. S, that is up to date, but it is very small. So is there a way, can we alter this data source A using the features of this small survey data set S? So in this problem, we use transformer. So the transformer model learns the conditional distribution of domain A. So it doesn't have to be labeled or unlabeled. We learn the conditional probabilities of A. And then we fine tune this transfer model with the data set S. And by doing this transfer learning from A to S, and the way we do the transfer learning, it actually catches the features of the data set A with S. And then we further fine tune this model with A. And then we get this administered data set. Now the question is, like, as an academic world that we live in, how do we evaluate? How can we say that the data alteration that we got does? So we are working on to this problem that mean standard deviation, variance, and so on. And Kerry, I've got enough time still?
You've got just a couple of minutes, Richi.
Okay, so I'll quickly talk about the third method, and I won't go into too much detail because the previous users have set the scene for GAN and a bit of the longitudinal data. So what our problem is that a lot of time in this longitudinal data, there is this missing data. But this missing data is on need basis. So for example, if we consider medical data, so a patient may miss lots of tests, but they miss it because they were not even told to do those tests. So this missingness in the data actually informs a lot of pattern in the data set. And at the same time, these temporal patterns that we get, they do not just depend on one time series, they depend on multiple time series. So for example, blood pressure and heart rate would have the high association among them. So how could we actually capture these global patterns in the data set that actually informs this missingness, and then we use this missingness for the early prediction? Because the problem in the medical domain or some of the education domain is how soon we can predict a person is sick or the person may likely to drop a school. So that's where we use GAN model. So we proposed an auxiliary GAN model for learning this data. So the way we do it, we actually input masked input, the target class and the static variables that we have got in the data. So it touches upon both static and dynamic variables. And the generator model then generates this imputed data that can be considered as fake, but the discriminator is then trained to differentiate between fake and real. But at the same time, we add another loss function to the discriminator that actually learns to classify the original data. So we present this original data to the classification, to the discriminator model. So it actually simultaneously learned this real fake loss at the same time classification loss, and it does it. So we have got quite a good results with auxiliary GAN that can perform early prediction as good as 80% in comparison to other discriminative or generative model that would only work around 20%. So in the end, I'd like to just acknowledge my research team as well. Thank you.
Thank you very much, Richi.